Hello my dear child and welcome to the next module of this particular chapter. Let's begin. Now over here we are going to discuss something called as molecules of elements and compounds. How exactly are we going to have that? Have a look. Now atoms of some elements have independent existence. These elements are considered to be monoatomic in the molecular state. So if a particular atom is absolutely stable, it has an independent existence. It does not want to combine with other elements. In that particular case, the molecule of that particular substance is going to be monoatomic in nature. Who are the examples over here? The perfect example are the two noble gases, helium and neon. They have a perfect electronic configuration, a stable electronic configuration. They neither lose electrons nor do they gain electrons, as a result of which a helium atom is a helium molecule. A neon atom is a neon molecule. And what kind of molecules are they? Monoatomic molecules. Who do we have next? Sometimes, however, two or more atoms of an element combine to form molecules of that particular element itself. Such elements are in the polyatomic molecular state. Any part of an atom, when it combines with more than one atom of itself, will become polyatomic in nature. So the problem is a single atom of that particular element is not that stable. It combines with other atoms of the same element so as to become a polyatomic molecule and to exist in the polyatomic molecular state. Examples, let's have a look. Who do we have first? In the case of diatomic substances, we have oxygen and nitrogen. So we never write down the formula of oxygen as O, it's unstable. We write down the formula for oxygen as O2 in the diatomic state. Nitrogen, a single atom of nitrogen is unstable. So we write down diatomic nitrogen as a single nitrogen molecule. Then we have ozone given by the formula O3. Three atoms of oxygen combine to give you a single molecule of ozone which is absolutely stable. And then we have phosphorus given as P4, which means that four atoms of phosphorus will combine to give you a single molecule of phosphorus. And we have octatomic sulfur. 8 atoms of sulfur combine to give you a single molecule of sulfur. All of these, diatomic, triatomic, polyatomic, they are all examples of the polyatomic molecular state. Okay. Now when atoms of different elements are going to combine with each other, the molecules of the compounds are formed. Very evident. Let's have a look. For example, we have water given by the formula H2O. 2 atoms of hydrogen, 1 atom of oxygen combine to give you a single molecule of water. Carbon dioxide, single atom of carbon, 2 atoms of oxygen to give you a single molecule of carbon dioxide. So here we have hydrogen and oxygen, carbon and oxygen, two different elements combining together to give you a single molecule of that particular compound. Now, molecular mass and the concept of a mole, very important, and we are going to make it super easy for you. Let's have a look. What is molecular mass exactly? The molecular mass of the substance is nothing but the sum of the atomic masses of all the atoms present in a single molecule of that substance. Now what does that mean? Say suppose I have a molecule of carbon dioxide. It contains an atom of carbon and it contains 2 atoms of oxygen. I know what is the weight of a single atom of carbon. I know what is the weight of a single atom of oxygen. If I add up the individual atomic masses of all the atoms present in a particular molecule, I will be getting the molecular mass of that particular substance. And don't worry, we are going to give you examples for the same. Now, understand that molecular mass, what is it exactly? What is the formula? Sum total of the individual atomic masses of all the atoms which are present in a particular molecule. Like atomic mass, molecular mass is also represented in the unit Dalton. So atomic mass, what is the unit? Dalton. Molecular mass, what is the unit? Dalton, because molecular mass is nothing but the sum total of all the atomic masses. So the unit is going to be exactly the same. The symbol is going to be U as given onto the screen right now. Now, let's calculate molecular mass of carbon dioxide. It can be deduced as follows. I'm going to help you out. We'll take it slowly, we'll take it step by step, and we'll make it super interesting and easy for you. Okay. Now, when we talk about carbon dioxide, we first need to write down the formula for the molecule. What is the formula? Carbon dioxide, CO2. Who is the first element? Carbon. When you talk about carbon, what is the atomic mass of carbon, as you can see on the sheet over here? 12. So in that particular case, carbon dioxide, a single atom of carbon weighs 12. How many atoms of carbon are present in carbon dioxide? CO2, single atom, so 1. Therefore, what do? We take the atomic mass and multiply it by the number of atoms. 12 into 1. How much will that give you? 12. So, how much amount of mass will a single atom of carbon contribute in carbon dioxide? 12. That's the answer. Now, we need to do it for oxygen. Slightly tricky. One or two things are going to change. We have oxygen. Atomic mass is 16, as you can see over here. How many atoms of oxygen are there? 2. So, 16 is the weight contributed by one atom, but since I have two atoms, 16 into 2. Now, 16 into 2 gives me 32, which means in a molecule of carbon dioxide, 12 is contributed by a single atom of carbon, 32 is contributed by both the atoms of oxygen together. Now, what do you need to do? We have 12 for carbon, we have 32 for oxygen, add them up together to give you the molecular mass, which is going to be 44. As simple as that. 12 is the weight of one atom of carbon and 16 is the weight of one atom of oxygen. But since we have 2, we multiplied 16 into 2 to give me 32. 12 plus 32 gives me 44 as my final answer. That's my first sum. Very easy to understand. Let's go with another example so that the concept becomes even more clear. Now, molecular formula for nitric acid is HNO3 and we need the molecular weight, molecular mass of nitric acid. How are we going to do? Let's look at the molecule first. What is the formula? HNO3. Something that we already know. It's already given in the sum. Who's the first element? Hydrogen. In HNO3, there is a single atom of hydrogen. So 1. Apart from that, one atom of hydrogen weighs 1. So 1 into 1. What is the mass of the constituent? 1. Who do we have next? Nitrogen. Weight of one atom? 14. How many atoms of nitrogen are there in HNO3? HNO3, N, 1 atom of nitrogen. So 14 into 1 gives me 14. Great, perfect. Slightly tricky. Think, nitric acid, HNO3. For oxygen, the weight of one atom is 16, but there are 3 over there. So 16 into 3 gives me 48. What do we have to do now? Simply add up all of these masses. 48 plus 14 is 62. 62 plus 1 is 63 and that gives me my final answer. The molecular mass of nitric acid is going to be 63. As simple as that. Okay. So now let's continue for mole concept. We know that atomic mass, which is the molecular mass of certain monoatomic molecules. Carbon is a monoatomic molecule, sodium is a monoatomic molecule, calcium is a monoatomic molecule, having the bases of 12, 23 and 40 respectively. Similarly, molecular masses of elemental molecules. Hydrogen, one atom weighs 1, there are 2 atoms, so 1 into 2 is 2. Nitrogen, N2, one atom weighs 14, but there are 2 atoms, so 14 into 2, 28. Oxygen, one atom weighs 16, but there are 2 atoms, so 16 into 2, 32. Molecular masses of certain compounds. For water, one atom is the mass of hydrogen, there are 2 of those, so 1 into 2. 16 is the weight of oxygen, so plus 16 gives me 18. For carbon dioxide and nitric acid, I have already calculated in this particular module for you. So, one molecule of water is 18, one molecule of carbon dioxide is 44, one molecule of nitric acid is 63, something that we've already done. But now, let's give these weight a deeper meaning and let them connect to the concept mole. Now, what am I going to do? If I take 12 grams of carbon, I have 1 mole of carbon. 23 grams of sodium, I have 1 mole of sodium. 40 grams of calcium, I have 1 mole of calcium. Similarly, 2 grams of hydrogen is 1 mole of hydrogen. 28 grams of nitrogen is 1 mole of nitrogen. Oxygen, 32 grams of oxygen is 1 mole of oxygen. And we could do exactly in the last part over here. 18 grams of water is 1 mole of water. 1 mole of carbon dioxide is 44 grams. 1 mole of nitric acid is 63 grams. As simple as that. So, let's conclude. 1 mole of a compound is the mass of that particular substance in grams. equal in magnitude to its molecular mass. So if you find out the 1 mole of any substance, what do? You take that particular substance, calculate its molecular mass, and when you calculate the number of the molecular mass, what is the unit? Gram. In that particular case, when you do that, you will be getting the mole of that particular substance. The SI unit is obviously mole. So 1 mole of any compound is the mass of that particular substance, but in grams, and just calculate the molecular mass for that particular compound, put the unit as grams. So say suppose you want it for nitric acid. First what do? Calculate the molecular mass. You get the answer as 63. 63 grams of nitric acid will be 1 mole of nitric acid. As simple as that. Okay. Now we know that number of moles of a substance is denoted by the letter N, small n. How do we calculate the number of moles? Very simple, we have a formula for that. Mass of the substance in grams. So basically whatever mass of the substance has been given to you, divided by the molecular mass of the substance. That is something you can calculate. So whatever amount of mass for a particular substance has been given to you, divide it by the molecular mass of that substance, that you can calculate. When you do that, that is going to give you your answer for 1 mole of that particular substance. How many moles are there? Finally, one must understand Avogadro's number. A mole of any substance, whatever substance is there, will always contain 6.022 into 10 raised to 23 molecules. I repeat, 1 mole of any substance will contain 6.022 into 10 raised to 23 molecules. Let's try to make sense of this information. 1 mole is so many molecules. That's something we know, right? So say suppose I have water. I want to calculate how many grams of water will make 1 mole. What do? I calculate the molecular mass. 1 into 2 for the 2 atoms of hydrogen, 16 into 1 for the 1 atom of oxygen. 2 plus 16, 18. 18 grams of water is 1 mole of water. And that 1 mole of water will contain 6.022 into 10 raised to 23 molecules of water. For carbon dioxide, first calculate the molecular mass. Carbon is 12 into 1, single atom, so 12 into 1. Oxygen is 2 atoms, so 16 into 2, 32. 12 plus 32, 44. 44 grams of carbon dioxide is 1 mole of carbon dioxide. And 1 mole of any substance contains 6.022 into 10 raised to 23 molecules of that substance. So if I take 44 grams of carbon dioxide, that 44 grams of carbon dioxide will exactly contain 6.022 into 10 raised to 23 molecules of carbon dioxide. Interesting, isn't it? 18 grams of water contains the same number of molecules of water as present in 44 grams of carbon dioxide. So 18 grams of water contains Avogadro's number of molecules of water. 44 grams of carbon dioxide contains Avogadro's number of molecules of carbon dioxide. Okay, let's finish off. We know in 1 dozen we have a total of 12. So 12 of any substance is obviously going to give you a dozen. A gross is 144. So 144 nails over here, 144 nails of iron. I can say I have 1 gross of iron nails. But for 1 mole, the number is way bigger. 6.022 into 10 raised to 23 in numbers, atoms, molecules, ions, so as the case may be. Okay, so let's finish off. Number of particles, atoms, ions, molecules, it could really be anything, doesn't matter, is the number of moles of that particular substance into Avogadro's number. Let's put it in the form of an equation. What is number of moles of a substance? How do we represent it? By the letter small n. And Avogadro's number is represented as capital N A. So the small n over here is the number of moles of that particular substance into Avogadro's number. That will give you the number of particles present in any substance, atoms, ions or molecules, so as the case may be.